Welcome to the week 1 video 2, and in this video we are going to talk about the steps that lead to an action potential in a neuron. So let's go back and remember that the resting membrane potential is the state of the neuron and especially the axon when it's at rest. So there's been no stimulus, it's its resting state. And remember that the inside is negative and sitting at about negative 70 millivolts compared to the outside of the cell. So right here I have a couple of slides. These are two of my own slides. They're not in your slide deck, and that's okay. But what they're talking about are the steps before an action potential. And specifically, they're actually talking about what happens in areas like the dendrites, which is the receiving end of a neuron. And when these types of stimuli affect the dendrite, you may or may not get an action potential that will shoot down the axon to the axon terminals. So notice that this top part talks about a stimulus. So this stimulus comes in to this neuron from another cell or another neuron, and it's going to make the gated ion channels open. Sometimes this type of stimulus goes by some other names, like a receptor potential, a generated potential, a postsynaptic potential. So there's a lot of names that we might use to describe what's happening at the receiving end of this neuron. So it's getting signals from other neurons or cells that are around it. What makes these type of potentials different from an action potential, why it's called a graded potential, is because the strength of the potential is not all or none, and the strength of the potential is dependent on the stimulus that comes in. But when that stimulus comes in and it causes a small potential across this dendrite, it doesn't last very long. It causes the ions to move through their leak channels, but it's a very short distance. So let's see what some of those kind of look like in a graph. The graded potential, we see a depolarizing one over here and a hyperpolarizing. So let's start by defining those terms. Our resting membrane potential is minus 70 millivolts. Depolarization is when the cell on the inside, remember we're always talking about the inside of the cell relative to the outside, when the inside of the cell becomes more positive. So notice we move from minus 70 up closer to minus 60 in this figure. So this is a depolarizing graded potential. It's causing the inside of the cell to become less negative or more positive, however you like to think about it. Over here we have a hyperpolarizing potential. In this case, we have the inside of the cell becoming more negative than the negative 70 that it was at resting. So we're getting closer to negative 80. Now, when you're talking about the dendrites or the cell bodies, we're not talking about what's happening at the axon yet. That's going to be coming up in just 1 minute. But at the dendrites and the cell bodies, these type of potentials can summate. That means they can be additive, so adding on top of each other, or they might cancel each other out. You might have a depolarizing potential with a hyperpolarizing potential. And what we haven't gotten to yet, but we will a little bit later, is these type of potentials can happen from different types of neurotransmitters that may interact with that neuron. So let's look at what we have in this picture. Again, defining depolarizing as becoming more positive and hyperpolarizing as becoming more negative. Notice we have some potentials here that are small, little potentials. These are graded potentials. Remember I said at last slide that they could be called postsynaptic. So an excitatory postsynaptic potential is one that brings you closer to threshold, closer to the point of actually forming an action potential. An inhibitory postsynaptic potential is one that brings you further from threshold and actually makes the inside more negative. So if you have an inhibitory postsynaptic potential, you are unlikely to form an action potential. In other words, you are unlikely to send that signal. However, if you have a lot of excitatory postsynaptic potentials, these can summate and you may hit the threshold level of excitation. And once threshold has been met, the action potential will form. So we have a couple things over here on the left. Most of that I've already talked about. And we're going to talk again about what is special about threshold. Threshold is the point at which an action potential will occur, and it has to do with the sodium channels that are opening. So what we have in an excitatory postsynaptic potential is we have sodium channels opening. Sodium is going to be changing the positive nature of this cell. It's making it more positive as sodium comes into the cell. Sodium's coming in, and a little bit's coming in and a little bit's coming in. But if you get enough that you reach this threshold point, then a massive amount of sodium comes in, and that's what causes this positive. So we have a couple slides to demonstrate that for you through the next couple of them. This one is just another picture. We have the same thing going on of the inside of the cell. We have a depolarizing potential and we have a hyperpolarizing potential. So just be very, very clear on the terms depolarization and repolarization. They will be very important terms for you to understand. So let's see what happens to the axon if we form an action potential. We're going to talk about the movement of the ions in just a minute. But overall, kind of big picture right here, if we form an action potential at the area of the neuron called the axon hillock, it's basically right here where the axon meets the cell body, then at the axon hillock, if an action potential forms, it's going to shoot the signal down the axon. So that's why it's really important, because we call it a nerve impulse, or the signal that the neuron is going to send. What's happening when you have an action potential is a massive reverse of the membrane potential. Notice that we have sodiums rushing in, and we go from -70 up to about +30, and that's a difference of about 100 millivolts. So it's a huge difference in the electrical charge across the membrane of this cell. So we have tons and tons of sodium, and they rush in so fast, very fast. And that massive change then actually sends the signal down. Now, how does it do that? Because right here, right, we have some of those voltage-gated sodium channels. Do you remember we talked about voltage-gated? If you get enough of a change in the voltage of a membrane, they may open. Well, right here we have voltage-gated sodium channels. Those open when you have the membrane potential near becoming more positive. Once those open, then you get a massive amount of sodium. Remember, there's sodium out here, right outside this axon. Tons and tons of sodium are in the extracellular fluid. So when you get the sodium gates opening, tons of sodium are coming in, and now right here, if we move down, that's exactly what has happened. So a bunch of sodium has come in, and now we've moved the action potential from this area down to this area, and that's how it's going to continue to move its way down the axon, is just by opening those voltage-gated sodium channels as you continue to move along the length of the axon. But remember that you have to reach that threshold. If it's not strong enough to reach threshold, and threshold is about -55 or -55 millivolts, then you will not have a strong enough impulse to open those voltage-gated sodium channels. So here we have reminders of what's going on at rest. We have voltage-gated sodium channels and potassium channels are all closed. That's resting membrane potential. But with depolarization, that's our first step, we open those voltage-gated sodium channels and sodium enters the neuron. Once you get up to that maximum positive millivolts, that's about +30, Then those voltage-gated sodium channels close. And then we have to return the neuron back to its resting state. How does that happen? During the stage of repolarization, that's when the voltage-gated potassium channels open. And potassium will leave or efflux and out of the neuron. It will leave the neuron. And that will help as the positive, of course, potassium is a positive ion. As the positive ion leaves the inside of the cell goes and becomes more negative, and more negative. And we also have the help of the sodium-potassium pump. Remember, pushing 3 sodiums out for every 2 potassiums that it lets in. So let's look at a couple different examples of those action potentials. I put this slide in this deck, not because I'm going to go over it necessarily, but just to highlight that there's a great action potential video for you to watch on Access Medicine that we've linked into your PowerPoint. So please check that out. I love these pictures of the action potentials because they show you so much that's going on. We see the level of threshold that's being met, and in the text here, it's telling us what's happening to the ions. So down here at -70, we're at resting. I actually wish they had put this line down here and shown how it goes up, but it's an illustration. So we're over here at resting membrane potential, and we have probably some excitatory postsynaptic potentials that are beginning to reach toward threshold towards that -55. And once we hit that -55, right this point, like this literal space right here before we shoot up, that's where we open the voltage-gated sodium channels. And sodium rushes into the cell so super fast. So very fast. Because it's a positive ion going inside of the cell and the inside's negative, we see that we become drastically less negative and more positive as we push our way up to the top of this action potential. And this is an all or none event. Once you open these voltage-gated sodium channels, they cannot half open. They fully open, and when they do, sodium rushes in. It's like a trigger on a gun. You can't go backwards and you can't partially pull it. You either do or you don't. And so the sodium rushes in. What's going on with this number 2 right here? This says potassium channels are opening and potassium begins to leave. Now, potassium channels are opening right here, but they're actually pretty slow. So sodium channels are fast and potassium channels are pretty slow. So there's not much potassium leaving just yet. But we're going to see that happening kind of a lot more in number 4. So this line that goes from 1 to 2 up to 3, this phase, and we're going to see it in a couple slides here, this is called the depolarization phase. So when you're asked what's happening in depolarization, sodium channels are opening and sodium's rushing into the cell. By the time we get to the top, somewhere around positive 30 millivolts or so, this one says positive 40, it's an approximate, but we usually talk about at the top, somewhere around positive 30, the sodium channels become refractory. What does that mean? They're closing. They're closing and no more sodium is coming in. And in fact, they're closing so that sodium can't come in anymore. And now we see the potassium. Now that all the sodium's already entered, there's no more to come in, the potassium begins to efflux. So over here, depolarization, we have sodium influx. Over here, this side is repolarization. We have potassium efflux. Potassium is leaving the cell. Potassium's going out through those potassium channels. Potassium's leaving, and it's as a positive ion leaves the inside of the cell, we become more negative on the inside. That's again what we're measuring. We become more negative, we become more negative. What's this little dip? This little dip that happens, this little hyperpolarization, happens because the potassium channels, even though they're closing, remember how they were slow to open? They're kind of slow to close as well. So we get a little bit too much potassium leaving than we have intended to have according to where we want to go for our resting membrane potential. So we have a little bit extra potassium that leaves, but that's okay. That dip is normal. And then the sodium potassium pump is going to help us get back to our resting. On this slide, I want to highlight just a couple things. A reminder about a video that you can watch, which will help. Again, the more resources that you have, the better off you are. Each of these color-coded phases is showing you a little bit more about when your sodium channels are opening. What's happening at this phase? These are primarily chemically based sodium channels. That's why it's this little yellow. This is the postsynaptic graded potential, and it hasn't hit threshold. The moment we move from yellow to green and we shoot up, that's this phase right here, and these are our voltage gated sodium channels that are opening. Then they close up at the top and we enter repolarization, which is the entire blue highlighted phase. Here, potassium leaves the cell and we begin to bring it back to our resting state. I included this one in the video just to show you the initial stimulus has to reach threshold in order to form an action potential. You may have small stimuli. On occasion, a neuron may be stimulated by some other neurons or other cells, but they don't reach enough of a voltage change. If they don't, then they fizzle out into nothing. So these particular depolarizations, these small depolarizations, would not cause this neuron to send a signal at all, because it just goes back to resting. It's only the stimulus that reaches the threshold level that opens the voltage-gated sodium channels that are going to cause an action potential to form. This picture is from your textbook. It is a very, very good figure in physiology. I love these. I love how they show you multiple things that are happening at the same time. Here's how you look at a figure like this. Down here we have the action potential. The action potential is in this black line. Sodium and potassium is showing you their movement in the red and the purple line. So you see sodium heavily moving in that red. So look at how slow potassium is. So it's very late to do anything, which is why its effect is at the refractory time or the repolarization time. Up here, we have the opening and closing of the channels. So you can kind of line yourself up to figure out, all right, at this stage, what's happening? Well, we're at resting membrane potential. Nothing's happening right here at stage kind of time 0. Resting time, channels are closed, but then we start to move over here. We've got some sodium channels that are open. These sodium channels are letting some sodium in. And then when we hit threshold, we open lots of sodium channels. So we begin to see what's going on with that action potential. And then bringing it back down, we open the potassium channels. Now we have a lot more potassium moving over here than we do sodium. Of course, the sodium channels are closed by now. So this is telling us a little bit also that we haven't talked about the excitability, right? So the excitability of this neuron is very high. It has a potential right here to be excitable. Down here, it's going through the process, so its excitability is 0. It can't be excited again. It's in the middle of it. And over here, it's building it back up again. That relates to these terms absolute and relative refractory period. The absolute refractory period is the time in which the neuron absolutely cannot be stimulated again. The reason is because it hasn't been brought back to a resting state yet. If you haven't moved all your ions across the membrane, then you can't let the millivolts change significantly. Over here in the relative time, that's where you're almost back to your resting state. You've almost got your ions where they need to go at rest to be ready for another action potential. So with a strong enough stimulus, a neuron can be stimulated again during the relative refractory period. So listen carefully. A neuron cannot be stimulated again during the absolute refractory period, but it can be stimulated again during the relative refractory period. So I have just a couple more slides, and in each of those, a quick little quiz type question to see if you're following along with the information that's been in this video. Please make sure to spend a long time studying through the action potential, that you know what's going on with the ions and their movements at every phase, at the depolarization, threshold, depolarization to action potential, repolarization, hyperpolarization, and movement back to resting. It's really, really important that you go through each of those stages and that you know what's happening to the channels and to the ions and to the neurons millivolts at that time. So here's one question for you to see if you're following along and understanding what's going on. Neurons will generally repolarize once the membrane potential reaches approximately positive 30 millivolts because. So where are we when this happens? We're at the top. So if we want to kind of draw a rough little action potential, sorry about that, and then kind of like that. So here's our rough little action potential. Here we are at about positive 30. So why does it generally repolarize? Why do we enter this downward phase at that time? Is it because voltage-gated sodium channel gates close? Well, they are certainly closing up at that time, but because they're closing, we don't have sodium moving though. So how is that going to get us to become more negative? So even though the statement is true that voltage-gated sodium channels are closed up there, that's not actually what's going to get us to go back to our resting and cause the repolarization. All right, what about some other ones? Voltage-gated potassium channels open. So that is another true statement. They are open. In fact, they opened a little bit over here, but they were just slow. So now that they're fully open and our potassium is moving, potassium's leaving the cell. If a positive ion leaves the cell, then you are going to begin to repolarize. So yes, actually, if you've had a chance to look at them while I was explaining, the answer to this question is B. Let's talk about what's going on with C and D. C is talking about chemically gated sodium channels. Well, chemically gated sodium channels are involved way down here in the initial postsynaptic potential, the one that may lead to an action potential. But chemically gated channels aren't involved in an action potential in this phase, either depolarization or repolarization of the action potential itself. So it can't be C. And then D. Well, in this particular chapter, we actually haven't talked about calcium channels at all. We're going to talk about them a little bit with neurotransmitters, but calcium channels are not what's causing the action potential of a neuron. So the answer to this question is B. All right, here's our last one. You would expect a neuron that depolarizes to negative 65 millivolts would do what? Negative 65. So if our resting membrane potential is negative 70, and we get to negative 65, we become a little bit positive, but not very much. So let's look through our choices. We can return to a resting membrane potential without generating an action potential, fire a much more intense action potential with a peak of plus 100, fire a less intense action potential with a peak of plus 15, or we're going to hyperpolarize. So of these answer choices, I hope that you picked out answer A. Answer A is the correct one. If you have negative 65 millivolts, you have not reached threshold. Threshold is negative 55 millivolts. So you've had a small graded potential, even a graded depolarization, but it's not been enough to hit negative 55, not been enough to hit that threshold mark, so you did not form an action potential. So in fact, what will happen is you will return to resting. Let's talk about B and C though. I want you to remember that an action potential is an all or none event, but it is almost always the same all or none event. In other words, it gets up to about positive 30 millivolts, and it doesn't matter how much more you talk about trying to be intense or less intense, those aren't possible things. You cannot have a more intense or a less intense action potential. You can only have an action potential. It's always the same intensity. It always goes up to about positive 30 and then repolarizes back down. So it doesn't matter whether you've had 1,000 neurons that are trying to depolarize one other one, or you have one neuron. You can't have a more intense or a less intense. So just this statement right here makes both of these wrong, and therefore you can't reach a positive 100 or a positive 15. Those things aren't possible. Then over here, why would the neuron not necessarily hyperpolarize? Well, there's nothing to cause it to become more negative on the inside. It just doesn't hit its action potential. So I hope that's been helpful in your understanding of the action potential.